Imagine standing on dry grass in eastern Africa, and the sky has two bright things in it. One of them is the moon, the other one is not. It is a hard white point, high overhead, too small to have any shape, too bright to look at comfortably, and it throws a second shadow at your feet, thinner than the moon's with a sharper edge. When the moon sets, that shadow stays. It does not flicker. It does not move against the stars in any way a lifetime could measure. It has hung there every clear night since long before your grandmother was born, and it will outlast everyone you know. Nothing alive on this planet can know what it is, or that it is passing, or that it is pulling something loose far above your head that will still be arriving 2.5 million years from now. So what was it, and what did it leave behind? By the end of tonight you will know exactly what came through, and why the danger it started is far from over. Get cozy, subscribe if you have not, and stick around, because the thing that Encounter actually damaged is not what everybody reaches for. Let's dive in. Part 1. The Second Light. There is a night, about 2.5 million years ago on the high grassland of eastern Africa, when the sky has two bright things in it. One of them is the moon, low and thin in the west, doing what the moon has always done. The other one is not the moon, and it is not a planet, and it is not anything that has a name yet, because nothing alive on this planet has invented names. It sits high overhead, and it is a point rather than a disk, too small to have any shape at all no matter how long you stare, and it is bright enough that looking directly at it is uncomfortable, the way looking at a welding arc across a room is uncomfortable. It is white, and it is hard-edged, and it is the second brightest thing in the sky. If you were standing there in the dry grass, you would notice something strange about the ground at your feet. You would have two shadows. The moon gives you one, soft and grey and familiar. The other light gives you a second one, fainter, but with a sharper edge, falling in a different direction. When the moon sets, that second shadow stays. The light does not flicker. It does not move against the stars in any way that a lifetime of watching could detect. You could be born under it, grow old under it, and die under it, and it would be in the same place among the same stars on your last night as it was on your first. It does not go away. It is simply there, every clear night, for longer than anything resembling memory can hold. Generations of creatures are born, live their whole lives, and die beneath a sky that has a second sun in it, and not one of them ever sees the sky without it, and not one of them can know what it is. Nothing on the planet at that moment has any way of knowing that the light is a star, that the star is passing, that it is moving at roughly 30 kilometers every second, that it is on its way through the outermost territory of our own solar system, or that as it goes it is quietly dragging at objects 40,000 times further from the ground than the ground is from the sun. Nothing there can know that the encounter will leave consequences, and that those consequences will still be arriving 2.5 million years later, and that they will be arriving now. That is the story tonight. A star came through. It has a catalogue number. And the reason it matters is not that it happened, but that it has not finished happening. Let me be precise about what is and is not being claimed here, because this is the sort of topic where the claims tend to get inflated in the retelling, and I would rather start on solid ground. The idea that other stars occasionally pass close to the sun is not speculation. It is bookkeeping. We have a catalogue of the positions and the motions of tens of millions of stars, accurate enough that we can wind the whole thing backward like a film and ask which of them have been near us and when. That work has been done, and it has been done carefully, and it produces a list. On that list, near the very top, sits an ordinary star that almost nobody outside the field has ever heard of. What is new, and what this whole video is really about, is that in the summer of 2026, 2 researchers published a paper arguing that we can see the wreckage, not the star. The star is long gone, 246 light-years away by now and receding, indifferent, its own business entirely. The wreckage, the debris. the specific, identifiable, still arriving consequences of a gravitational shove delivered before there was anybody here to feel it. And the wreckage, in this case, is comets. Here is the shape of the argument, and I want to lay it out plainly before we go anywhere near the details, because the details are genuinely lovely, and they land much harder if you already know what they are details of. Out past the planets, out past Pluto, out past the point where the sun stops being able to hold a candle to the cold, there is a reservoir of frozen objects. Not thousands of them, not millions, something on the order of 1 trillion. They are the leftovers of the solar system's construction, flung outward 4.5 billion years ago and stranded there ever since, and they are so far away and so cold that we have never seen a single one of them in place. Not one. Everything we believe about that reservoir has been worked out from the tiny number of its members that fall back inward and become comets. Every so often one does. It comes in, it warms, it grows a tail, somebody photographs it, and it goes back out. And here is the thing the two researchers noticed. If you take the comets that are arriving right now for the very first time, the genuinely new ones, the ones that have never been near the sun before in the entire history of the solar system, and you plot the orientations of their orbits, they are arriving from too many directions at once. Not from the direction they should, not with the lopsidedness they should have. From everywhere, more or less evenly, more or less at random, as though something had grabbed the whole reservoir and shaken it. The Milky Way is supposed to leave a fingerprint on those comets. It is a specific fingerprint, it is predictable, and people have been predicting it for 40 years. In 2026, somebody finally went and checked whether it was there. It was not there, so something else did this. Something recent, something local, something strong enough to override the gravity of 100 billion stars, and crucially something that is still in the process of delivering its results, because objects in that reservoir take millions of years just to fall inward once, which means we are not looking back at an event, we are standing in the middle of one. I want you to hold on to that image from the beginning, the one with 2 shadows on the grass, because we are going to come back to it. By the time we do, you will know exactly how bright that light was, to within about a magnitude. You will know how long it hung there. You will know what was alive underneath it, and it was not us, and it was not even one single kind of creature, but at least 4 different kinds of almost people sharing the same continent at the same time. And you will know the honest answer to the question in the title, what the danger actually is, and why it is far from over, which turns out not to be the answer most people reach for, and is a great deal stranger. But we cannot start with the star, we have to start with the place it went through. Because the whole case rests on the behaviour of objects in a region that no telescope has ever resolved, that no spacecraft will reach for another 300 years, and that we know about at all only because a Dutch astronomer in 1950 noticed something odd about where comets come from. Part 2. The comets that came from everywhere. Before we go out to that reservoir, and we are going, and it is the strangest place in the solar system, you should know who noticed this, and what exactly it was they noticed, because the way this discovery happened is not the way you would expect. Nobody was looking for a star. On the 2nd of July 2026, a paper appeared in a journal called the Planetary Science Journal. Its title is the sort of title that scientists write when they are being scrupulously careful about how much they are claiming, and it reads, "A potential signature of HD 7977's passage among observed long-period comet orbits." Note the word potential. Note the word signature. These are people hedging in the title, which is usually a sign that they know exactly how strong their evidence is and have decided not to oversell it. The authors were Nathan Kaib at the Planetary Science Institute in Tucson, Arizona, and Sean Raymond at an astrophysics laboratory in Bordeaux, in France. And what they had done was, in a sense, embarrassingly simple. They had gone to the catalogues of known comets, catalogues that have been sitting there for decades, filled in correctly by hundreds of different people, nothing hidden, nothing secret, and they had plotted one particular number. This is worth sitting with for a moment, because it says something about how discovery actually works, There was no new telescope, there was no new instrument, no new survey, no dramatic night at the eyepiece. The data had been public for 30 years. What was new was somebody asking a question the data happened to be able to answer. To understand the question, you need one distinction, and it is the only piece of jargon in this whole video that really matters. Comets, the long-period ones that come in from the outer reservoir, fall into two groups. The first group are the ones we call dynamically new. A dynamically new comet is a genuine first-timer. It has never been here before. Not once in 4.5 billion years has it come close enough to the Sun to be warmed, to be pushed around by the gravity of Jupiter and Saturn, to lose any of its original ices. It is arriving right now on its first pass, carrying an orbit that is still more or less the orbit it had out in the cold. Technically, it is defined by having an original orbit larger than about 10,000 times the distance from the Earth to the Sun. And to put that number in some kind of human perspective, 10,000 times the Earth-Sun distance is roughly 200 times further out than Pluto ever gets. The second group are what the field calls young returning comets. These have been through the inner solar system a handful of times already. Their orbits sit between about 1,000 and 10,000 times the Earth-Sun distance. They have been warmed. They have been kicked around by the giant planets. They are not pristine, and their orbits carry the marks of having been here before. Two populations, two histories. And that turns out to be the single most important fact in this entire story, though we will not see why for another hour. The samples Kybe and Raymond worked with were not enormous, and I want to be honest about that from the start. 107 dynamically new comets, taken from a European catalogue that specialises in carefully computed original orbits. 112 young returning comets, taken from the orbital database maintained at the Jet Propulsion Laboratory. 219 objects in total. That is not a huge number of things. It is, however, essentially every well-measured object of its kind that we have, which is a different problem entirely, and one we will come back to at the end. There is also a cut-off in the data that tells you something rather charming about the history of astronomy. Both samples only include comets discovered after 1989. The reason is that before about 1990, comet discovery was dominated by amateurs, dedicated people sweeping the sky with their own telescopes, from their own gardens, in whatever direction they happened to prefer. Which means the pre-1990 catalogue of comets is not a sample of the sky. It is a sample of where enthusiasts pointed. After 1990, systematic automated surveys took over, sweeping the whole sky methodically, and the catalogue stops being a record of human habits and starts being a record of the universe. If you want to say something statistical about comets, you have to throw away everything found before the machines took over. So, 107 pristine first-timers, all discovered by systematic surveys, all with carefully reconstructed original orbits, and Kybe and Raymond plotted the orientations of those orbits relative to the plane of our galaxy. They should have come out lopsided. Instead, they came out even. Comets arriving from every direction at once, in a distribution so close to random that when you test it against a perfectly even spread of orientations, it fits beautifully. When you test it against the lopsided pattern that 40 years of theory says it must have, it fails. And the first thing they did, to their credit, was try to make the result go away. Because there is an obvious boring explanation available, and any careful person reaches for it first. Reconstructing the original orbit of a comet is delicate work. You're watching an object for a few months near the Sun, while it is actively spraying gas in every direction, and from that you're trying to work out the shape of a path that took it millions of years to travel. Errors are unavoidable. And if your orbits are sloppy enough, you would expect the orientations to smear out toward randomness whether or not anything actually interfered. The evenness could be nothing but measurement noise wearing a costume, so they tightened the quality requirement. The original sample allowed a certain tolerance in how precisely each comet's original orbit had been pinned down. They cut that tolerance by a factor of 25, threw away every comet whose orbit was not exquisitely determined, and ran the whole test again on what survived. The evenness did not budge, Sharpening the data did not sharpen the pattern back into existence, which is exactly what you would see if the pattern had never been there, and exactly the opposite of what you would see if fuzzy measurements had been washing it out. The result was not an artifact of imprecision. It was in the sky. Now, I have not yet told you why anyone expected lopsidedness, and I'm going to make you wait for that, because it is the most satisfying piece of physics in this story, and it deserves a proper introduction. But I can tell you what the failure means in the broadest terms, and it is this: something interfered. The orientations of those orbits are not random noise, they are a record. Every one of those comets was sitting out in the cold on some particular path, and whatever pushed it inward left its handwriting on the orbit it arrived with. If the handwriting matches the galaxy did it. If the handwriting matches nothing, then something else did it. Something more recent, something more local, something strong enough to overwrite the influence of 100 billion stars. And here is the move that makes this paper different from everything that came before it. For as long as astronomers have known that stars pass near the sun, the research has run in one direction. You start with the stars. You measure their positions and their motions. You rewind them. You find the ones that came close, and then you calculate what they must have done to our comets. The star is the input. The comets are the predicted output. Dozens of papers have been written this way, and they are perfectly good papers. Kaib and Raymond ran it backward. They started with the comets, with the actual, observed, catalogued debris, and asked what must have been done to produce it, and then they went looking for a suspect that fit. That is forensics rather than prediction, and it has a different flavour of persuasiveness. Anyone can look at a passing star and calculate that it probably stirred something. It is a much harder and much more interesting thing to look at the stirring and work out which star did it. The suspect in this case left the scene 2.5 million years ago and is now 246 light-years away, entirely beyond reach, and will never be examined directly by anybody. But the debris is still coming in. Some of it arrived this decade, some of it will arrive next century, which is a genuinely unusual situation when you think about it. We are not doing archaeology here, sifting through the settled remains of something finished. The event is still running. The comets that astronomers will discover in the 2030s and the 2040s and the 2200s are, if this paper is right, still part of the same disturbance, still falling inward along paths that were set before anything that could be called human existed. There is no moment at which the encounter will be over, and we can start studying it in the past tense. So that is the case. An anomaly in a public catalogue, spotted by two people plotting an old number a new way, pointing at a star that has already gone, describing an event that has not stopped. Everything from here is a matter of working out whether it holds up. And to do that, we have to go where the comets came from, out past the planets, out past the heliopause, out to a place so far away and so faint that in 75 years of looking, nobody has ever managed to photograph a single object in it, and where our fastest machine will not arrive for 300 more. Part 3. The cloud we have never seen. The largest structure in our solar system has never been photographed. I want to be careful about how I say that, because it sounds like the setup for something mystical, and it is not. It is a plain statement about the limits of instruments. There is a shell of frozen objects surrounding the sun, and it is so much bigger than everything else here that if you drew the orbits of the planets to scale on a page, the planets would be a smudge in the middle too small to see. And in 75 years of trying, nobody has ever managed to detect a single one of its members in place, not with Hubble, not with the largest telescopes on the ground, not with the James Webb Space Telescope, which can see galaxies that formed in the first few 100 million years after the Big Bang, and cannot see an object the size of a mountain sitting in our own backyard, because the object is cold and dark and roughly 1,000 times further away than Neptune. We know it is there. We have known for 75 years, and every single thing we believe about it has been deduced rather than observed. You cannot see the Oort cloud, you can only see what falls out of it. That sentence is the whole methodology of the field, and for most of the last century it has been a point of pride. One of the genuinely elegant pieces of reasoning in astronomy, an entire structure inferred from indirect evidence with nothing but arithmetic and patience. Hold on to it anyway. We're going to come back to that sentence much later, and by then it will have stopped being a compliment. The deduction was published on the 13th of January 1950 in a journal called the Bulletin of the Astronomical Institutes of the Netherlands by a Dutch astronomer named Jan Oort. The paper is titled The Structure of the Cloud of Comets Surrounding the Solar System and Hypothesis Concerning Its Origin, which is a title that gives away the ending, and it was built on two observations that anyone could have made and nobody had put together. The first observation was about how far out comets go. When a long-period comet swings past the Sun, you can measure its path, and from that path you can calculate where it has come from, how far out its orbit reaches before it turns around and falls back. Oort did this for every comet he had, and he noticed that the answers clustered. They were not scattered randomly across every possible distance. They piled up out at tens of thousands of times the distance between the Earth and the Sun, which is a strange thing for a random assortment of objects to do. It suggested a source at a particular distance feeding them in. The second observation was about direction, and it is the one that settles the shape. Comets do not arrive along the plane of the planets. Everything else in the solar system is flat. The planets orbit in more or less the same plane, the asteroid belt sits in that plane, the Kuiper belt out past Neptune is flattened too. If comets came from a disk, they would arrive from disk directions. They do not. They come in from everywhere, from above, from below, from every angle with roughly equal frequency. A flat structure cannot produce that. A sphere can. So Oort concluded that the Sun is surrounded in every direction by a general cloud of comets. His own estimate was about 100 billion objects large enough to be observable, and a total mass somewhere between 1/10 and 1/100th of the Earth's, which, as we will see, is dramatically lower than anything modern work suggests, and is a useful reminder of how much of this is inference stacked on inference. He was not quite first, and the person he beat deserves a mention. 18 years earlier, in 1932, an Estonian astronomer named Ernst Öpik published a paper working out how impulses from passing stars affect comets on very stretched orbits. He concluded that a comet could stay gravitationally bound to the Sun out to about 1,000,000 times the Earth-Sun distance, roughly 16 light-years, which is 4 times further away than the nearest star, and that passing stars would progressively lift comet orbits into exactly the distant bound reservoir Oort would later describe. Öpik had the physics and the mechanism 2 decades early. Oort got the name. Some of the literature calls it the Öpik-Oort cloud, and honestly it should. Now, the numbers. And I want to flag in advance that the numbers in this section are soft, that the published literature disagrees with itself about most of them, and that anyone who quotes them to you with great confidence is overselling. The cloud is usually described as occupying the space between about 5,000 and 100,000 times the Earth-Sun distance. The inner edge is thought to sit somewhere between 2,000 and 5,000. The outer edge is placed anywhere from 10,000 to 100,000, depending on whose paper you're reading. Beyond about 100,000 to 200,000, the Sun simply loses the argument. The gravity of the Milky Way is stronger out there than the gravity of the star at the centre of our own system, and anything that far out is not really ours anymore. For population, the current working figure is around 1 trillion objects larger than a kilometre across in the outer cloud, with possibly several times that number in the inner region, though the ratio between inner and outer is one of the least settled numbers in the whole field, with published estimates ranging from about 1 to about 200. For mass, estimates run from 1 Earth mass to 100, with a commonly quoted middle figure of about 5. Early estimates went as high as 380. The honest position, and the one the researchers themselves take, is that the relationship between how bright a comet looks and how much it weighs is poorly understood, so the mass of the Oort cloud is not actually known. The temperature out there is about 4 degrees above absolute zero. That is not a small number that has been rounded down. That is essentially the temperature of empty space. The leftover heat of the Big Bang, spread evenly across the whole universe, sits at 2.7 degrees above absolute zero, and out in the Oort cloud the sun contributes so little on top of that background that it barely registers. Nobody has measured it. It is an estimate from first principles, and it matters more than it sounds, because ices that survive at 4 degrees include substances that would boil away instantly anywhere near the planets, which is exactly why a first-time comet can brighten so violently and so unpredictably when it finally comes in. It is not just melting, it is releasing things that have never been warm. But here is the number that actually explains this entire video, and it is the one nobody expects. The escape velocity from the sun falls off with distance, and out in the Oort cloud it becomes almost nothing. At 10,000 times the Earth-Sun distance, the speed you need to break free of the sun entirely is 0.4 of a kilometre per second. At 100,000, it is about 13/100ths. To put that in terms you can feel, a rifle bullet leaves the barrel at around a kilometre per second. Out there, a rifle bullet fired away from the sun would simply leave and never come back. That is the crucial structural fact about the Oort cloud. It is enormous, it holds 1 trillion objects, and it is held together by essentially nothing. These are not objects locked into stable orbits by a firm gravitational grip. They are drifting, at walking pace, at the very outer limit of what the sun can still claim, and the smallest nudge from outside can change where they go. Which brings us to the last thing in this section, and it is a matter of scale, because I do not think the numbers convey it on their own. Here is the way the people at NASA describe the distances, and I like it because it uses time instead of length. Sunlight takes 8 minutes to reach the Earth. It takes about 4.5 hours to reach the orbit of Neptune. It takes about 17 hours to reach the heliopause, the boundary where the sun's outward wind finally gets stopped by the pressure of interstellar space, the boundary that Voyager 1 crossed in 2012, and which people quite reasonably described at the time as leaving the solar system. And then, from there, sunlight travels for another 10 to 28 days before it reaches the inner edge of the Oort cloud, and perhaps 1.5 years before it passes beyond the outer edge. 1.5 years of light, going the whole way. Voyager 1 is the furthest object human beings have ever launched. It is currently around 170 times further from the sun than the Earth is, travelling at about 17 kilometres per second, which works out to roughly 1 million miles a day. NASA has calculated the precise moment it reaches 1 full light day of distance from Earth, the 18th of November 2026, and NASA's own estimate for the rest of the journey is this. At its current speed, Voyager 1 will not enter the Oort cloud for about 300 years, and it will not exit the far side for something like 30,000. 30,000 years at 1 million miles a day to cross the region we're talking about. The star we're chasing crossed it in a few thousand. Part 4. The Tide That Combs. The Cloud. Here is a question that sounds simple and is not. If those objects are drifting out there at walking pace, held by almost nothing, why do we not get comets constantly? Why is the sky not full of them all the time? And the answer is that in a sense it is, just very slowly, and the thing responsible is not a passing star at all. Most of the comets we have ever recorded were not sent here by any dramatic event. They were sent here by the galaxy. The mechanism is called the galactic tide, and it is the same physics as the tide in the ocean, which I think is the most pleasing fact in this whole subject. The moon does not pull the sea up. The moon pulls on the whole Earth, and it pulls very slightly harder on the side of the Earth nearest to it than on the side furthest away. And it is that difference, not the pull, the difference across the width of the object, that raises the water. Tides are about gradients. Now do the same thing on a scale that is difficult to hold in your head. The sun sits inside the Milky Way, roughly 26,000 light-years out from the centre, embedded in a flattened disk of a few 100 billion stars and an enormous quantity of gas. All of that mass pulls on our solar system, and it pulls very slightly harder on the near side of the Oort cloud than on the far side because the near side is closer to the mass of the disk. The Oort cloud is nearly a light-year across, which is more than enough width for that difference to be real. That difference is the galactic tide, and it has been leaning on our comets for 4.5 billion years. Two astronomers, Julia Heisler and Scott Tremaine, worked out the details in 1986 in a paper in the journal Icarus, and their central finding was about direction. Because the galaxy is a flattened disk rather than a sphere, the tide is not the same in every direction. The dominant component is vertical, perpendicular to the plane of the galaxy, set by how much mass is packed into the disk near us. That vertical component is roughly 10 times more effective at delivering comets than the sideways components. The galaxy pulls comets down and up out of the cloud far more efficiently than it pulls them in or out. But the crucial subtlety is what the tide actually does, and it is not what you would guess. The tide does not push comets inward. It never gives a comet a shove toward the sun. What it does is torque the orbit, twist it gradually, changing the tilt and the orientation of the ellipse, and as the orientation changes, the closest point of that orbit slowly migrates. An object whose closest approach to the Sun was 40,000 times the Earth-Sun distance can have that closest point walked inward over enormous spans of time until eventually it dips into the region of the planets and becomes a comet we can see. And here is where the fingerprint comes from, which is the thing I've been promising you for 20 minutes. Whether the tide walks a comet's closest approach inward or outward depends on how that comet's orbit is oriented relative to the plane of the galaxy. Some orientations get pulled toward the Sun, other orientations get pushed away. It is not random, it is determined cleanly by geometry, and it is the same for every object out there, which means the comets that arrive have been selected. They are not a fair sample of the cloud, they are specifically the ones whose orbits happen to be oriented in the way the tide could work on, because those are the only ones the tide could deliver. So the population that shows up in our telescopes should be lopsided, strongly lopsided. Roughly 2/3 of them should fall on one side of that geometric divide, and only about 1/3 on the other. That is the prediction. It has been in the literature since the 1980s. It is not a vague expectation. It is a specific, testable, numerical claim about the sky. Remember it, because in about 10 minutes we're going to find out what happens when you check. I want you to feel the timescale first, though, because the number is meaningless until you do. Imagine you're sitting on one of these objects. Pick one at 40,000 times the Earth-Sun distance, comfortably out in the middle of the cloud. It is a lump of ice and dust and rock, maybe a few kilometers across, and it is dark, and it has never in its existence been warm. The Sun from here is a bright star and nothing more. You could cover it with a fingernail held at arm's length. It gives you no heat you could measure, no disk you could resolve, no day and no night. The sky around you is essentially the same sky you would see between the stars, because functionally that is where you are. You are moving, but you're moving at a few tenths of a kilometre per second, slower than a passenger jet, and the galaxy is leaning on you so gently that in a human lifetime nothing measurable happens at all. Nothing happens in 10,000 human lifetimes. Now compress the clock. Run 100 million years past yourself and watch the closest point of your orbit creep inward. 10 times the Earth-Sun distance for every 27 million years that pass. In the time it took for the first primates to appear and diversify and produce everything with hands, your orbit has shifted by an amount you would struggle to notice on a diagram. That is the galactic tide. It is not an event, it is a pressure. And the only reason any comet ever reaches us is that it has had 4.5 billion years of being leaned on. Now, that timescale has a consequence that turns out to be everything, and it comes from how the effect scales with distance. The torque weakens as the inverse square of the size of the orbit. Halve the orbit and the tide becomes 4 times less effective. Which means that while the tide works reasonably well on objects far out at 50 or 100,000 times the Earth-Sun distance, it becomes almost useless further in. Down at 10 or 20,000, you need 100 million years or more to move a comet's closest approach appreciably, and full cycles of that motion can take billions of years. So the inner part of the cloud is effectively locked. The tide cannot get material out of it, Not because the material is held firmly, we establish that it is barely held at all, but because the only mechanism available is too slow to matter. Astronomers have a formal way of describing this. They talk about the loss cone, which is just the range of orbits whose closest approach is small enough that we would actually see the object as a comet. The question is whether that range is kept full or kept empty. And in 2008, a group led by Hans Rieckmann ran 1 million simulated comets across the entire age of the solar system, with both the tide and passing stars included, to find out. Their answer is stark. For objects with orbits smaller than about 20,000 times the Earth-Sun distance, the observable loss cone is less than 1% full. For objects out at 100,000 and beyond, it is essentially 100% full, continuously topped up, always supplying. Picture that as plumbing, because that is what it is. The outer cloud is a tap left slightly open, running a thin, steady trickle that has not stopped in 4.5 billion years. The inner cloud is a reservoir with a blocked outlet, enormous, full, and going nowhere, which tells you exactly what a passing star does. It does not simply add comets to the flow, it opens the valve. It reaches into the part of the cloud that the galaxy cannot touch, and releases material that would otherwise have stayed out there indefinitely. That is the difference between a stellar flyby and business as usual, and it is why one of these events can matter for millions of years afterward. One more thing before we go and look at what the check actually found. Rieckmann's group also noticed that the tide and the passing stars do not simply add up. Working together, they inject significantly more comets than the sum of what each would manage alone. The stars lift orbits into positions where the tide can finish the job, so you cannot separate the two cleanly. The system is not a sum of parts. And a final caution, because there is a tempting idea here that has caused a great deal of trouble. The sun does not sit still in the galaxy. It bobs up and down through the galactic plane every 85 million years or so. It swings in and out radially every 149 million, and it takes something like 210 to 225 million years to go around once. And since the tide depends on where you are in the disk, it is extremely tempting to conclude that the comet supply must rise and fall on a clean schedule. People concluded exactly that for decades and built some very dramatic theories on top of it. In 2011, a group led by Josh Gardner settled it properly and found something much less satisfying. The variation is real, but it is quasi-periodic rather than periodic. It amounts to only about 30%, and it is driven mostly by the sun's radial motion rather than its bobbing. 30% and messy is a long way from clockwork, which matters because in 2026 somebody finally checked the fingerprint, and what they found was not 30% and messy, it was gone. Part 5. The fingerprint that wasn't there. Let me put the prediction and the measurement next to each other, because the whole video turns on this one comparison, and I do not want it buried in qualifications. The prediction, from the physics of the galactic tide, is that roughly 2/3 of the comets arriving on their first pass should fall on one side of a particular geometric divide, and roughly 1/3 on the other. 2-to-1, lopsided. The measurement, from 107 comets, is 48.6%. 48.6% is a coin flip. It is not a slightly weaker version of the prediction, not 2/3 shaded down to 60% by some complicating factor. It is the complete absence of the thing that was supposed to be there. Whatever selection process the theory says must have shaped this population, that process has left no trace in it whatsoever. Before we ask what that means, I want to be honest with you about how strong this result actually is, because I think the honesty is more interesting than the drama, and because this channel is not in the business of overselling a p-value. The researchers ran 2 standard statistical tests to compare the observed comets against the simulated tide-driven population. The first is called a Kolmogorov-Smirnov test, and it returned 0.0039. The second is an Anderson-Darling test, and it returned 0.0035. What those numbers mean, roughly, is that if the tide really were responsible for these comets, you would expect to see a mismatch this bad about 4 times in 1,000. The paper describes this as rejecting the tide-only explanation with nearly 3 sigma confidence. And here is the honest framing of 3 sigma. In particle physics, 3 sigma is not a discovery. It is called an interesting hint, and the reason it has that name is that 3 sigma results evaporate roughly as often as they survive. Physicists have a long and slightly painful history of 3 sigma effects that generated headlines and then quietly dissolved when more data arrived. So this is a serious result. With a sample of 107 objects and a specific prior prediction, it is a genuinely serious result. But it is not a settled fact, and anybody presenting it to you as proven is going beyond what the authors themselves claim. They chose the word potential for their own title. There is also a piece of history that makes the failure land harder, and it is worth knowing before we go on, because it means the prediction was not invented for this paper and then found wanting. It had already been confirmed. Back in 1987, an astronomer named Armand Delcem pointed out that the galactic tide should leave its mark not just in the orientations of comet orbits, but in where on the sky comets appear to come from, that there should be zones of avoidance, directions the comets conspicuously do not arrive from, near the plane of the galaxy and near the galactic poles, because those are the geometries where the torque is weakest. Then, in 2004, 2 researchers named John Matisse and Jacques Lissauer went looking for the orientation version of the same signature and found it. They found the lopsidedness in both the first-time comets and the returning ones in about the proportion the theory demanded, and in 2022 Nathan Kaib, the same Kaib who is one of the authors of the 2026 paper, extended the finding to a further population of distant comets whose closest approaches sit out near the orbit of Saturn, and found the tidal signature there too. So this was a prediction with a track record. It had been made, tested and confirmed more than once by different people, using different samples across 3.5 decades, which is what makes it genuinely interesting that when the best available modern catalogue of pristine first-time comets was finally put through the same test, the signature that had been showing up reliably for 35 years simply was not in it. That said, there is a detail here that makes this considerably harder to dismiss than a typical 3 sigma wobble, and it is the most persuasive thing in the entire paper. They did not only test the first-time comets, they tested the other population too, the young returning ones, the 112 objects that have already been through the inner solar system a handful of times, and those fit the galactic tide beautifully. The same test, applied to the returning comets against the same simulation, returned 0.57. That is about as clean a match as you can hope for. It means there is no reason whatsoever to doubt the tide model when you apply it to that population. The lopsidedness the theory predicts is right there, in the returning comets, in exactly the proportion the physics says it should be. Now think about what that does to the possible explanations. If both populations had failed to match, the obvious conclusion would have been that the simulation was simply wrong. And that would have been a perfectly reasonable conclusion, because these simulations are elaborate and full of assumptions. The team modelled 1 million test particles with starting orbits spread from 3,000 to 50,000 times the Earth-Sun distance, integrated across the full age of the solar system, with the giant planets in place and comet brightness fading modelled by a rule of thumb from the 1950s. There are a dozen places in that setup where you could hide a mistake. If everything had come out wrong, the machine would be the suspect. But everything did not come out wrong. The machine reproduced one population almost perfectly and failed on the other. A model that succeeds exactly where it should succeed and fails exactly where something unusual is suspected is in a completely different evidential category from a model that fails everywhere. It has, in effect, passed its own control test. And to close off the last easy escape route, remember what we said earlier. They tightened the orbital quality requirements by a factor of 25, discarded every comet whose original orbit was not exquisitely determined, and the evenness did not budge. So this is not the fingerprint being smeared out by imprecise measurements. There is no fingerprint to smear. There is one more test worth mentioning, and it is the one that makes the result feel almost too tidy. They took the observed first-time comets, and compared them not against the tide model, but against a perfectly even, perfectly random distribution of orbital orientations, the pattern you would get if something had thoroughly scrambled the whole population with no regard for geometry at all. That test returned 0.47, a good fit. The comets arriving from every direction at once are not merely failing to be lopsided. They are, as far as the data can tell, genuinely random, so the shape of the puzzle is now precise, and it is stranger than a simple anomaly. We have two populations of comets, drawn from the same reservoir, arriving in the same era, observed by the same surveys. One of them obeys the galaxy exactly as predicted. The other looks like it was shaken in a jar. Any explanation has to account for both, not for a general failure, but for a split. And there are only two ways out that anybody has been able to construct. The first is that something came through and stirred the cloud. That is the explanation we are chasing, and it will occupy the rest of this video. The second possibility is quieter, and in some ways more unsettling, and the paper is careful not to dismiss it. It is that nothing unusual happened at all, that no star came close, that the tide has been the only thing operating for millions of years, and that the reason the first-time comets look random is that the Oort cloud itself is shaped differently from what we have believed. Specifically, that it is far less concentrated toward its centre than the standard model of how it formed predicts. If the cloud's material is distributed more evenly across all those distances, then the mix of comets the tide delivers changes, and you can get closer to an even distribution without any visitor at all. I want to sit with that alternative for a second, because it is a genuine fork in the road, and it is easy to skate past it in the excitement of hunting a star. If the second explanation is right, then there was no dramatic encounter, no bright second sun over the savannah, no comet shower. Instead, 4 decades of modelling how the Oort cloud assembled itself, work that goes back to a foundational paper in 1987 and has been refined by half a dozen groups since, would be wrong about the resulting shape. That is arguably a bigger problem than a flyby. A flyby is an accident. A wrongly shaped cloud is a broken theory. The reason the authors lean toward the star and lean only gently is arithmetic. When they test the flatter cloud scenario against the observations, the best agreement they can reach is about 0.03, better than the standard tide model, but still poor and still in tension with everything the formation models predict. When they test the flyby scenario, they can do considerably better. Neither option is comfortable. One of them is less uncomfortable, which means the next question is not really a question about comets at all. If a star did this, that star still exists. It is out there somewhere right now, going about its business, having moved on. And for the first time in the history of astronomy, we have a machine that can find it, not by looking for it, but by taking the motions of tens of millions of stars and running the entire sky backward like a film, until we see which one of them was standing next to us at the right moment. Part 6. Rewinding 30 million stars. For almost the whole history of astronomy, the sky was a picture, a beautiful one, and one we learned an enormous amount from, but a picture, a flat arrangement of points of light from which you could work out brightness and colour and, with real effort and a great deal of cleverness, distance. What you could not easily get was motion, and without motion, the sky has no past and no future. It is just an arrangement. Then the European Space Agency launched a spacecraft called Gaia, and the sky stopped being a picture and became a film. Gaia was not a camera in the sense that Hubble is a camera. It was a measuring instrument, and what it measured was position. Obsessively, repeatedly, for more than a decade, spinning slowly and sweeping the same stars over and over, building up a record of exactly where each one sat, and exactly how that position drifted from year to year. It also measured how fast stars were moving toward or away from us, using the shift in their light. And when you have both of those things for the same star, you have something remarkable. You have 6 numbers, 3 for where it is, 3 for how it is moving. Position and velocity fully specified in 3 dimensions. 6 numbers per star is all you need to run time backward. The precision involved is difficult to convey without sounding like an advertisement, so let me try it with a comparison. Gaia sat about 1.5 million kilometers from Earth, at a gravitational balance point where it could keep the Sun, the Earth and the Moon all behind it and stare into the dark, and it measured stellar positions to a precision of a few tens of microarc seconds. A microarc second is a millionth of a second of arc, and a second of arc is already a 3600th of a degree. At that precision, from the distance of the Moon, you could measure the width of a human hair. Applied to a star, it means you can detect a sideways drift of a few meters per second, at distances of hundreds of light years, which is what makes reconstructing the encounter possible at all, and the reconstruction got better in stages, which is worth knowing because it explains why this story is being told now rather than a decade ago. Gaia's second data release in 2018 had complete 6-dimensional data for about 7.2 million stars. From that, Baylor Jones and his colleagues found 694 stars whose paths bring them within 5 parsecs of the Sun, 26 with at least a 50% chance of coming inside 1 parsec, and 7 inside half a parsec. Useful, but thin. The third release, 4 years later, had that same complete information for more than 4 times as many stars, and the encounter distances for individual objects tightened dramatically. In the case of the star we are chasing, by nearly a factor of 7 between one release and the next. That is the part I think is genuinely wonderful, and it is worth being clear about why it works. Stars in the solar neighbourhood are not doing anything complicated. Over a span of a few million years, they travel in almost straight lines at almost constant speeds. There is no chaos to speak of, nothing that needs enormous computing power, no sensitive dependence on initial conditions that ruins your answer after 1,000 years. If you know where a star is and how it is moving, you can simply subtract, run the motion in reverse, work out where it was 1 million years ago, and 2 million, and 3. Do that for every star at once, and you have a reversible model of the neighbourhood. Gaia's third data release, published in June of 2022, contained complete 6-dimensional information, position and velocity, the full set, for 33,653,049 stars. 33 million stars, each with a reconstructible history. And so the obvious question became answerable for the first time. Win the whole thing back and ask, which of these has ever been closer to us than it is now, and how close did it get? The astronomer who ran that search is named Corinne Baylor Jones at the Max Planck Institute for Astronomy in Heidelberg, and he published the results in 2022. It is essentially a census of visitors. Every star we have adequate data for that has come near the Sun in the recent past, or will come near it in the near future. And the first thing to say about the results is how careful he was, because the carefulness is the reason we can trust them. 61 stars in that catalogue formally come within 1 parsec of the Sun. A parsec is about 3¼ light years, so that is the standard threshold for a genuinely close encounter. But Baylor Jones does not report 61. He reports that he has high confidence in only 42 of them, about 2/3. The remaining 19 he sets aside because when he looked at them individually, some had measurement problems and some turned out to be members of wide binary systems, where the star's motion is being disturbed by an unseen companion in a way that corrupts the calculation. That distinction is going to matter enormously in about 10 minutes, so file it away. Unrecognized companions wreck these reconstructions. Tighten the threshold and the numbers drop fast. 13 stars have come, or will come, within half a parsec, 4 within a quarter. Now, those distances need context, because a parsec means nothing on its own. Here is the context. In our part of the galaxy, the average spacing between one stellar system and the next is about 2.2 parsecs, and the nearest star system to us right now, Alpha Centauri, is 1.3 parsecs away, which is close enough that it is the perpetual target of every serious proposal for interstellar travel anybody has ever drawn up. So when we start talking about a star that came within 300ths of a parsec, understand what that means. 0.03 of a parsec is roughly 70 times closer than our nearest neighbour is at this moment. It is not a near miss in the sense of two cars passing on a road. On the scale of the solar neighbourhood, it is a collision of territories, one star's outermost holdings ploughing straight through another's, and now the honest part, which I like this piece of work for. Having built the most complete catalogue of stellar encounters in history, Baylor-Jones declined to answer the most obvious question about it. If you want to know how often stars pass close to the Sun, a rate so many per million years, you cannot simply count the ones in your catalogue, because your catalogue is missing an enormous number of them. Faint stars, distant stars, stars without good velocity measurements. To convert a count into a rate, you have to estimate how much you are missing, and he judged that the incompleteness of the sample was too poorly characterized to do that responsibly. So he wrote, in effect, that this will have to be tackled with the larger sample expected in the fourth data release, and left the number blank. To give you a sense of how much is missing, before Gaia, of all the encounters within 5 parsecs that happened in a window of 5 million years either side of the present, only about 15% had been identified at all. 85% of our own recent stellar history was simply unknown, and a good deal of it still is. There is also something a little melancholy about the source of all this. Gaia is finished. The spacecraft stopped taking science observations on the 15th of January 2025 after more than a decade, and its operations were formally ended that March. Everything we're going to learn from it now, we will learn from data already collected, a fixed archive being worked through, with no possibility of going back for more. The film has been shot. What remains is the developing, and there is one more release to come, which becomes important because it means this entire story has an expiry date attached to it, a specific day on which the central claim either firms up or falls apart. We will get to that. For now, the point is simply this. Somewhere in that census of 42 trustworthy encounters, in the right window of time to have done what the Comets say was done, sat one object. Not a spectacular object, not a dying giant or a strange compact remnant or anything a survey would flag as interesting. An ordinary star of the same general kind as the Sun, catalogued for 174 years, that nobody had ever had the slightest reason to look at twice. Part 7. The Star in Cassiopeia. The star is called HD 7977, and I want to start with how thoroughly unremarkable it is, because that turns out to be the most interesting thing about it. It is a G-type dwarf, specifically a G3, which places it a hair hotter and a hair brighter than the Sun. Its mass is about 1.07 times the Sun's. Its radius is about 1.09 times the Sun's. Its absolute brightness, the figure astronomers use to compare stars stripped of the accident of distance, is around 4.64 against the Sun's 4.83. If you were shown the two of them side by side with the labels removed, you would need to look closely to tell which was which. This is, as near as this story could have hoped for, a copy of our own star. Right now, it is 246.9 light-years away, in the constellation Cassiopeia, the big lopsided W in the northern sky, the one everybody learns second after the Big Dipper, and at that distance it shines at about 9th magnitude, which means you cannot see it. Not on the darkest night from the best sight on Earth with the most adapted eyes. You need binoculars at minimum, and even then you would have no way of picking it out from the several hundred equally unremarkable points of light around it. Its names tell you something about how long it has been ignored. In Gaia's catalogue it is source number 5109116185692399040, which is not a name so much as an address. In the older German survey catalogue it is BD plus 61250. And it was first written down by an astronomer named Uelzen in 1852, as star number 1383 in a list. So this object has been on the books for 174 years, through the invention of photography, through the invention of spectroscopy, through the discovery that galaxies exist, through the entire 20th century. and in all that time nobody had the slightest reason to look at it twice. Then Gaia measured how it was moving, and it turned out to be the closest known past encounter between any star and the Sun. Not one of the closest. And it holds another distinction as well. Of every star we have adequate data for, it is the only one with a significant probability, 32%, of having come within 5/100ths of a parsec of us. Now, we have to talk about how close it actually got, and this is the part where I need you to hold 3 different numbers in your head at once without letting them blur together, because they come from 3 different methods and they do not agree. The first number comes from Gaia directly, via Baylor-Jones's census. Take the star's measured position and motion, wind it back, and the answer is a median closest approach of about 13,000 times the Earth-Sun distance, but with wide error bars. There is roughly a 5% chance it came inside 4,000, and roughly a 5% chance it never got closer than about 24,000. That is a range spanning a factor of 6, which for a measurement this important is uncomfortably loose. The second number comes from an independent analysis published in 2024 by a Polish group led by Piotr Dybczynski in the journal Astronomy and Astrophysics. Rather than compute a single trajectory, they generated 25,000 statistical clones of the star, each one consistent with the measurements but slightly different within the uncertainties, and flew all of them backward to see where they went. Their spread runs from about 2,500 at the 10th percentile to about 12,000 at the 90th, with a median around 6,400, noticeably closer than Baylor-Jones. And their paper contains a sentence that I think captures the strangeness of this whole subject better than anything else I read while preparing this. It is possible, they wrote, that 2.47 million years ago, a one solar mass star passed as close as 1,000 times the Earth-Sun distance from the Sun, and that such an event constitutes a kind of dynamical horizon for all studies of the past solar system's dynamics. A dynamical horizon, meaning a wall, meaning that if this happened, then calculations of how anything in the outer solar system was moving before that date become guesswork, because you cannot reconstruct the past through an event you cannot precisely characterize. There is a limit to how far back we can see, and the limit is not our instruments. It is one star going past, and the third number is the new one, the one this whole video is about. Keiben-Raymond's comet-derived figure, 6,000 to 10,000 times the Earth-Sun distance. Narrower than Gaia's range, sitting comfortably inside it, and arrived at by an entirely independent route, not from measuring the star at all, but from working backward from the debris. That is the thing worth appreciating. 2 completely different kinds of evidence, one from astrometry and one from comet orbits, converging on the same window. The date is similarly soft, and I would rather you know that than have me pretend otherwise. The paper says approximately 2.47 to 2.76 million years ago. Baylor-Jones's abstract says 2.8 million. Dybczynski's clones cluster at 2.47. When I say 2.5 million years, I am rounding a genuinely uncertain quantity to something a human brain can hold, and you should hear it as roughly 2.5 rather than exactly. So why is the uncertainty so large? We measured this star with the most precise astrometric instrument ever built. Why can we not pin it down? The answer is almost funny, and it comes down to a coincidence of geometry. HD 7977's motion across the sky is almost exactly 0. It sits there, year after year, essentially not drifting at all, and the signal-to-noise ratio on that measurement is only 4.2, which is to say, the quantity being measured is so close to nothing that the measurement is barely distinguishable from the noise. Here is the intuition. A star that appears not to be moving sideways at all is either coming almost directly toward you or going almost directly away. That is exactly the situation you want if you are hunting for close encounters, because it means the star's path lies nearly along your line of sight, and stars on such paths are the ones that pass close. But it is exactly the situation you do not want if you need precision, because the sideways speed is what tells you by how much it will miss. And when the sideways speed is nearly zero, small absolute errors become enormous fractional ones. A tiny mistake in a tiny number turns into a factor of 6 spread in the answer. We do know how fast it is travelling along our line of sight, and that part is well measured. About 26.8 kilometers per second by Gaia, with an independent measurement giving 29.9. Its relative speed at closest approach works out to around 30.6 kilometers per second. So it went past at roughly 30 kilometers per second, which is worth remembering. It is almost exactly the speed at which the Earth orbits the Sun. One thing we do not know about it, and would very much like to, is whether it has planets. No planet has been detected around HD 7977, but that is close to meaningless as evidence. At 246 light-years, with no dedicated campaign pointed at it, we would almost certainly have missed anything short of a large world on a short orbit. Given that it is a near twin of the Sun, the reasonable expectation is that it has some. Which means that for a few thousand years, two planetary systems were briefly sharing a neighbourhood, and whatever worlds it carried came through the outskirts of ours with it. And now the complication that could bring the entire structure down. Gaia produces, for every star it measures, a diagnostic number indicating how well that star's observations fit the assumption that it is a single object moving in a straight line. Values above about 1.25 mean the fit is poor and something is wrong. HD 7977's value is 2.01. The most common cause of a number like that is an unresolved companion, a second star, too close to separate from the first in any image, whose gravitational tug is swinging the primary around a shared centre of mass. And if that is what is happening here, then the tiny sideways motion Gaia measured is not the star's path through the galaxy at all. It is partly, or largely, orbital wobble, which would mean the trajectory is wrong, the encounter distance is wrong, and the whole reconstruction has to be redone. Dybczynski's group put this bluntly enough that it is worth quoting almost directly. In their assessment, none of the 3 Gaia proper motions published for this star are reliable, and the true error in the astrometric model is likely orders of magnitude larger than the formal uncertainties in the catalogue. Kaib and Raymond acknowledge it themselves, in their own paper, in plain language. While the star has no known companion, they write, it may still be unresolved, in which case the encounter distance range derived from Gaia data is unreliable, since it is currently being fitted with a single source model. So this is where we actually stand. There is a star. It is a near copy of the Sun. It came closer to us than anything else we know of, at a date we can bracket but not pin, along a path we have reconstructed from a measurement that is barely above the noise, and it may not even be one star. The suspect's alibi has never been checked, and yet something did make that light in the sky. Because whatever the exact number turns out to be, every version of this encounter, the closest, the furthest, and everything between, puts a sun-like star close enough that anything on Earth with eyes would have seen it. Part 8. What it looked like. From the ground. Let me stop for a moment and put the pieces back on the table, because we have covered a lot of ground, and the next part is the one I've been building toward from the first sentence. Here is where we are. There is an anomaly in a public catalogue. Comets arriving on their first pass are coming from every direction at once, when 40 years of confirmed theory says they must arrive lopsided. There is a reservoir those comets fall out of that nobody has ever seen, containing 1 trillion objects held by almost nothing. There is a mechanism, the galactic tide, that normally delivers them, that leaves a specific fingerprint and whose fingerprint is missing. There is a machine that let us rewind 33 million stars and find who was standing next to us. And there is a suspect, an unremarkable near twin of the Sun, in Cassiopeia, that came closer than anything else we know of, roughly 2.5 million years ago, which means we can now do something rather satisfying. We can work out what it looked like. The arithmetic is genuinely simple. It is one of the first equations an astronomy student learns. If you know how bright an object actually is, and you know how far away it is, you can calculate how bright it appears, And we know both. We know HD 7977's real brightness, because we can measure it now, and we have a range of distances for the encounter. Run the numbers for the window Kybe and Raymond favour, 6,000 to 10,000 times the Earth-Sun distance, and the star would have appeared at a magnitude of about -7 to -8. That number will mean nothing to most people, so let me anchor it against everything else in the sky. Venus, at its absolute brightest, when everything lines up perfectly, reaches about -4.9. It is the brightest thing in the night sky after the moon, bright enough that people file reports about it, bright enough to be seen in daylight if you know exactly where to look. HD 7977 at closest approach would have been somewhere between 6 and 18 times brighter than Venus has ever managed in the entire history of our species. Sirius is the brightest actual star in our sky, at -1.46. HD 7977 would have been between 180 and 500 times brighter than that, and the full moon sits at about -12.7, so the star would still have been somewhere between 75 and 210 times fainter than a full moon, which is important, and it is where popular accounts of this tend to go wrong. This was not a second moon. It did not light up the landscape or wash out the sky. Around it the night stayed dark and every other star stayed visible, and it is worth heading off a natural worry here, because bright sounds like hot, and in this case it was not. At 6,000 times the Earth-Sun distance, that star was 6,000 times further from the ground than our own sun is. Brightness falls off as the square of distance, so it was delivering something in the region of 36 million times less energy per square metre than the sun does. The sun drops roughly a kilowatt on every square metre of ground at midday. This star was delivering a fraction of 1,000th of a watt. It was spectacular to look at, and it did precisely nothing to the climate, and anyone telling you a passing star cooked or froze the Pleistocene is not doing arithmetic. Whatever this encounter did to Earth, it did not do it with light. Even at the far edge of Gaia's range, 25,000 times the Earth-Sun distance, the version where the star barely grazed us, it still comes out at about -4.9, which is to say that under every single version of this encounter, from the closest to the most distant, there was a new object in the sky, at least as bright as Venus at its best, and probably far brighter. So here is what it was like. You're standing outside at midday, and the sky is the ordinary blue of any afternoon, and there is a star in it. Not a smudge, not something you have to squint for. A hard white point, obviously there, sitting in the blue where nothing should be. You can find it without trying. It is up there while the sun is up. Then night. It rises with the stars, and it is the brightest thing in the sky, and it does not look like anything else in the sky, because everything else is a faint point and this is a fierce one. If your eyes are adapted and you hold a pale surface up, you can see the light landing on it. Objects have edges on the side facing it. If you stand still on bare ground, you have a shadow, thin and sharp, thrown by a star, and it does not move. That is the part that I find hardest to hold on to. Its apparent motion across the sky is around 7 minutes of arc per year, about a quarter of the width of the full moon annually. So over a long life you might notice it had drifted slightly against the pattern around it, if you were the sort of creature that tracked such things. On any given night it is nailed in place. It rises and sets with everything else. It is simply a permanent feature of the sky, as fixed and as ordinary as the stars in Cassiopeia are to us. And it lasts. At 30 kilometers per second, the star covers 1,000 times the Earth-Sun distance in about 155 years. So the whole approach and departure through the region where it outshone Venus runs on the order of 8,000 years, 4,000 or so of slow brightening and 4,000 of slow fading. Hundreds of generations. Nobody alive at any point in that window ever saw a sky without it, and nobody alive at any point in that window ever saw it change. Now, who was there? 2.5 million years ago in Eastern Africa, the answer is not one species but at least 4 at the same time. There was early Homo, our own genus, present by 2.78 million years ago at a site called Ledigararu in Ethiopia. There was Paranthropus, the robust Australopiths with the enormous chewing apparatus. There was Australopithecus garhi, dated to between 2.6 and 2.5 million years, which lands about as precisely on this event as the fossil record ever lands on anything. And there was a fourth kind of Australopithecus, a species distinct from everything previously known, which was only identified and described in 2025. 4 lineages of upright, tool-adjacent, small-brained hominins sharing a continent, and not one of them was Homo sapiens, which would not exist for another 2.2 million years. Some of them were already making stone tools. The oldest older one tools we have come from Gona, in Ethiopia, and date to about 2.6 million years, which produces one of the more disorienting facts in human origins. The oldest known stone tools are slightly older than the oldest known fossils of our own genus. Somebody was making them, and we are not entirely sure who. So the brightest object to appear in the sky in the entire existence of the genus Homo, brighter than any comet, any supernova recorded in history, anything in any chronicle or any myth, was witnessed continuously for thousands of years by at least 4 kinds of almost people who were already sophisticated enough to knap stone into cutting edges, and it left no record, none. Not a mark on a bone, not a scratched pattern, not a story, not a fragment of oral tradition, because none of those things existed yet. There was no writing for another 2.5 million years. There was no art for at least 2 million. Every creature capable of turning its face upward turned its face upward, night after night, for a span of time longer than our species has existed. And the total surviving evidence of that experience is a statistical wobble in the orbital elements of 107 comets. That is the whole legacy. A column of numbers in a catalogue, filled in by astronomers who had no idea what they were recording, describing the only trace left of the brightest thing our ancestors ever saw. Which raises the obvious question, and it is the question that saves this whole story from being a nice piece of theatre. A close pass makes a bright star, fine. Does it necessarily do anything else? Does proximity actually mean consequence? Because there is a control case. It happened much more recently, and the answer it gives is no. Part 9. The Star That Missed. 80,000 years ago, a star came closer to the Sun than any star we have ever documented. Closer, in the reckoning that was accepted for years, than HD 7977, and it did essentially nothing at all. Its catalogue designation is a mouthful, so everybody calls it Schultz's star, after the astronomer who found it. Ralph Dieter Schultz works at the Leibniz Institute for Astrophysics in Potsdam, and he reported it in a paper that went up in November of 2013 and was published in Astronomy and Astrophysics that January. The reason it had gone unnoticed until then is a small lesson in how easy it is to miss things that are right next door. It is 18th magnitude in visible light, which is to say astonishingly faint. It sits 2.3 degrees off the plane of the galaxy, which is one of the most crowded regions of sky there is. That crowded region is full of red objects, almost all of which are distant red giants rather than nearby dwarfs, and it has a low proper motion, and nearby stars are conventionally found by hunting for things that move quickly, because that is what being nearby usually implies. So it was faint, buried in a crowd, disguised as a common type of distant object, and moving in the way that distant things move, 4 separate reasons to overlook it, all at once. The thing that cracked it open was a mismatch between 2 velocities. Its motion across the sky is about 3 kilometers per second. Its motion along our line of sight is about 83, and a nearby star that is barely drifting sideways while hurtling toward or away from us is in a very particular situation. It is either coming almost straight at us or going almost straight away, which, if you think about the geometry, means it either has passed very close or is about to. Picture the 2 moments this discovery actually consisted of, because neither of them involve looking at anything. The first is a man at a desk in Potsdam in 2013, working through infrared survey data, noticing that the colours of one faint red smudge say nearby rather than distant, and writing it up as what it appears to be, an overlooked neighbour, 22 light-years away. No drama, a catalogue entry. The second is 2 years later at the University of Rochester, where an astronomer named Eric Mamajek and an undergraduate named Scott Barenfeld take that star's measured motion and run 10,000 simulated trajectories backward, each one nudged slightly within the uncertainties to see where they go. And they watch almost every single one of those 10,000 runs walk the star through the outer reaches of our Oort cloud. The number that matters is the tally. Of 10,000 simulations, 98% put it through the outer cloud, and exactly one out of 10,000, brought it into the inner region where the real damage gets done. Nobody saw anything. Nobody photographed anything. The closest stellar encounter in the whole of human history was discovered because a faint star was not moving sideways quickly enough. The published figures from that work were a closest approach of about 52,000 times the Earth-Sun distance, roughly 70,000 years ago, and those are the numbers you will still find quoted almost everywhere. They have been superseded. In 2019, a team led by Trent Dupuis improved the distance and motion measurements and revised the encounter to 68,700 times the Earth-Sun distance, 80,500 years ago, an improvement in accuracy of a full order of magnitude. So it was further out and slightly longer ago than the famous version. The system itself is a pair, a red dwarf of spectral class M9.5, with about 9.5% of the Sun's mass, orbited by a brown dwarf with about 6%, the two of them separated by less than the Earth-Sun distance, and going round each other every 8 years. Together they add up to roughly 14% of the mass of the Sun. They are currently 22 light-years away in the constellation Monoceros, and here is the detail that makes this encounter quietly sad. It was never visible. At closest approach it would have peaked at about 11th magnitude, around 100 times fainter than the faintest star the human eye can detect. Modern humans were alive and spreading across the world at the time. Not one of them ever saw it. The only caveat is that it is a magnetically active flare star, and objects like it have been observed to brighten by more than 9 magnitudes in an outburst, so it may have flickered into naked-eye visibility for minutes or hours on rare occasions. A star that appeared out of nothing and then vanished again, and nobody who saw it could ever have found it twice. Now the important part. Mamajek's published conclusion was that this passage likely caused negligible impact on the flux of long-period comets. Nathan Kaib, the same Kaib whose paper this whole video is about, is quoted saying he thinks the effect on the Oort cloud would be minimal, and the comparison Mamajek used to show why is the single best line in this entire subject. He calculated the gravitational acceleration that Schultz's star exerted on our solar system at closest approach, about 3.3 times 10 to the minus 13th meters per second squared. Then he calculated the acceleration the Moon exerts on the Earth, about 3.3 times 10 to the minus 5th. The Moon mattered 100 million times more, and in tidal terms, which is what actually stirs a cloud as we established, the Moon's influence was roughly 2 quadrillion times stronger. The closest stellar encounter in human history was, gravitationally speaking, less consequential than the tide going out. So proximity is not the story. What is? There is a single formula, and it explains everything in this video. The velocity kick a passing star delivers scales as its mass, divided by its speed multiplied by its distance. Mass over velocity times distance. 3 factors, and each one behaves the way you would expect except the middle one. Mass helps, obviously. HD 7977, at 1.07 solar masses, was about 8 times heavier than the whole Schultz binary. Closeness helps, obviously. HD 7977 came within perhaps 6 to 10,000 times the Earth-Sun distance. Schultz's star stayed out at 68,700, and slowness helps, which is the counterintuitive one, and the key to the rest of this story. Halve a star's speed and you double the kick it delivers, because the encounter simply lasts twice as long, and gravity has twice as long to work. Schultz's star went past at 83 kilometers per second and barely had time to pull on anything. HD 7977 crossed at about 30. Put all three together and HD 7977's impulse comes out larger by something on the order of 2 orders of magnitude. 8 times the mass, 3 times the crossing time, and roughly 1/10 of the distance. That is the difference between an encounter that opened the valve and an encounter that went past unnoticed, which inverts the intuition the whole subject arrives with. The dangerous star is not the one that pierces through at speed. It is the slow, heavy one that appears to be taking its time, the one that hangs there for thousands of years leaning. Hold that thought, because at the end of this video we are going to meet a star that is slower and closer than either of these, and we know exactly when it arrives. One last thing briefly, so this does not sound like pure theory. We have watched flybys happen elsewhere. Around a young star called UX Tauri, astronomers using the ALMA array found the disk drawn into spiral arms with a stream of gas bridging it to a companion that appears to be on an unbound orbit. A flyby caught in the act, roughly 1,000 years after closest approach. In the RW-Orighi system, there is a 600 astronomical unit arm of material trailing from the primary's disk, which modelling attributes to a recent close pass, and around a binary protostar called Z Canis Majoris. An intruder was identified about 4,700 astronomical units out, described by the lead researcher in plain terms. An object not bound to the system came into close proximity and interacted with the environment around it. Disks get visibly wrecked. This is not a hypothetical process. We just cannot normally see it happening to ourselves. Part 10. The shower we are standing in. So we have a suspect with the right mass, the right speed, and the right distance to have done real damage. But we still have that awkward split to explain. The one population of comets that obeys the galaxy perfectly, and the other that looks like it was shaken in a jar. And this is where the paper stops being a plausible story and starts being an argument, because the resolution of that split is not a hand wave. It is a clock. Here is how it works, in 3 steps. Step 1. A star passing at 6 to 10,000 times the Earth-Sun distance delivers a kick that is strong enough to completely randomize the orbital orientations of comets further out than about 20,000. Out there the objects are barely held, the star's pull dominates over everything else for the duration of the pass, and whatever careful geometry the galactic tide had spent 100 million years establishing gets wiped. Those comets come out of the encounter pointing in every direction, with no memory of what the tide had been doing to them. Step 2. But that same kick is not strong enough to do the same thing further in. Comets nearer 10,000 times the Earth-Sun distance are held more firmly and are further from the star's closest approach, so they get disturbed without being scrambled. They come out of the encounter shoved onto new paths, but still carrying some of the original lopsidedness the tide had given them. Now that combination is quite specific. A stronger encounter, a star coming closer or heavier or slower, would have randomized both groups. A weaker encounter would have randomized neither. Only a narrow window of impact parameters produces one scrambled population and one partly preserved population, and that window is what pins the distance to 6,000 to 10,000. The researchers found it by brute force. 13 separate simulations, each 3.5 million years long, with the star's closest approach stepped logarithmically from about 3,162 times the Earth-Sun distance all the way out to 50,119. 13 runs, and only the ones in that middle band reproduce what we actually see. And now step 3, which is the part I find genuinely beautiful. Those two groups do not arrive at the same time. An orbit's period depends on its size. Comets on smaller orbits come back sooner. Comets on bigger orbits take longer. Which means that when a star scatters material inward across a whole range of distances all at once, the resulting comets do not arrive as a single pulse. They arrive sorted. Smallest orbits first, largest orbits last, spread out over millions of years like runners finishing a race at wildly different speeds. So follow the consequence. the comets that were nearer in, the partly preserved ones that kept some of the tide's lopsidedness, those had shorter periods. They arrived first. They came in during the millions of years after the encounter, went round the Sun, got kicked about by Jupiter and Saturn, and are now on shorter orbits still. They are, in other words, exactly the population we call young returning comets, and they still look tide-sculpted because they are, and the comets that were further out, the thoroughly scrambled ones, those have periods of 2 to 3 million years, which means they are only reaching the inner solar system now, for the first time. They are the dynamically new comets, and they look randomized because they are. One event, 2 populations, 2 arrival times, 2 different signatures, both visible in the same decade, and here is the number that made me sit up when I read it. The dividing line between those 2 behaviours, in the simulations, sits at an orbit of about 18,400 times the Earth-Sun distance. An object on an orbit that size has a period of almost exactly 2.5 million years, which is when the star went past. The clock matches the crime. The comets currently arriving from every direction at once are not simply anomalous, they are time-stamped. Their evenness, combined with the length of their orbits, encodes when they were disturbed. It is very close to being able to read a date off the sky. You can watch the whole process in the simulations as a sequence. Immediately after the flyby, the newly injected comets sit on orbits of around 5,000 times the Earth-Sun distance. A million years later, the ones arriving have orbits of around 10,000. At 2 to 3 million years, now, the ones arriving have orbits of around 20,000. The reservoir is being emptied from the inside out, and we are watching a particular layer of it come through. And the test of whether all of this actually hangs together is not the story I've just told you. Stories are easy. But whether the numbers come out right when you run the simulation forward to the present day and look. So they did that. In the best-fitting run, at the epoch corresponding to now, 38% of the young returning comets fall on the negative side of that geometric divide, and 48% of the dynamically new ones do. Compare that with the sky. The observed dynamically new comets sit at 48.6%. The observed returning comets match a tide-dominated population, which is what a figure in the 30s means. The simulation is not roughly in the right area. It lands on both numbers at once, having been given nothing but a star of a particular mass, at a particular speed, at a particular distance, at a particular date. Getting there took some computational brute force, incidentally. 1 million test particles is not enough to produce a decent sample of comets when the baseline rate is as low as it is, so to boost the statistics they took 10 separate snapshots of their long-running simulation, spaced 100 million years apart and co-added them, building an effective population of around 10 million objects out of the same underlying physics. So how much extra material are we talking about? Averaged across the 2.5 million years since the encounter, for the range of distances that fits, the inner solar system has received something like 7 to 12 times as many long-period comets as it would have under the galactic tide alone. The paper's own conclusions compress that to an order of magnitude, which is a fair summary. And today, right now, at 2 to 3 million years after the event, the rate is about 2 to 2.5 times the quiet baseline. I want to be pedantic about those 2 numbers for a second, because they get conflated constantly in coverage of this result. The 7 to 12 figure is an average over the whole 2.5 million years, which includes the intense early phase. It is not a description of the present. The present-day figure is the factor of 2. If you hear somebody say we are currently getting 10 times as many comets as normal, they have merged 2 different statistics. The factor of 2 is the one that matters, and we are about to see why. As for how long it lasts, the drainage runs on different schedules for different depths. The comets on 10,000 unit orbits, the early arrivals, were flushed through within about 1 million years, 1 orbital period, and are long gone. The comets on orbits between 20 and 50,000 will not be fully cleared for another 3 to 10 million years. Kyb's own estimate, given to a magazine rather than in the paper, is that it will take 5 to 10 million years for the solar system to get back to normal. There is also a second wave behind the first, which is a detail I like because it shows how untidy the real process is. Some comets injected by the star did not come all the way in. They fell into the region of Jupiter and Saturn, got an energy kick from those planets that enlarged their orbits rather than shrinking them, and went back out onto longer paths, from which the galactic tide can inject them again on a later revolution. So the shower is not a single pulse followed by silence. It has an aftershock structure. Now let me give you the scale of what is actually being measured here, because I think it is easy to picture a sky full of comets, and that is not what this is. In a quiet, tide-dominated epoch, a simulation following 1 million test particles produces about 10 long-period comets per million years. 10. That is the baseline. This whole subject is the study of a trickle, and the 2026 result is the claim that the trickle is currently running at double speed. It is not a bombardment. It is a subtle change in a very small number, which is precisely why it took 30 years of catalogue data and 2 people plotting an old quantity, a new way to notice it. And how unusual is any of this? Here the honest answer is more deflating than you might expect, and it matters for how the video ends. Stars pass within 1 parsec of the Sun somewhere between 10 and 22 times per million years, depending on which survey and which completeness correction you trust. A 2026 study measured the rate of passages within half a parsec at about 2.6 per million years, which works out to roughly 12,000 such flybys over the 4.5 billion years the solar system has existed. Passages as close as 10,000 times the Earth-Sun distance, the class we are discussing, happen roughly 20 times per billion years, about once every 50 million years, and encounters strong enough to shift the average comet flux by 10 or 20% happen every 5 to 10 million years, which means the comet supply has never actually been steady. It varies by tens of percent on million-year timescales as an ordinary matter of course, and the notion of a calm, tide-dominated solar system may be a convenience rather than a description. Against all of that, though, this particular encounter stands out. Kaib and Raymond's assessment, if their reconstruction holds, is that HD 7977's passage was the most powerful stellar encounter the solar system has experienced in the past 100 to 300 million years. Not the closest we know of. That record depends on which numbers you use. The most powerful, the one that moved the most material. Which brings us to the consequence that nobody was looking for, and the one that I think is the real story here. Because if the comet flux we have been measuring for the last 3 centuries has been running at double its normal rate, then something else follows. Something about a number that appears in every textbook, that has been quoted confidently for 75 years, and that was never right. Part 11. The number that was never real. You cannot see the Oort cloud. You can only see what falls out of it. I said that an hour ago, and I said it admiringly, because it is one of the genuinely elegant pieces of reasoning in the history of astronomy. An entire structure, the largest in the solar system, deduced from nothing but the behaviour of the handful of objects that leave it. A Dutchman in 1950, working with a modest list of comet orbits and a pencil, correctly inferred the existence of 1 trillion objects nobody would ever photograph. Now, I want you to hear the same sentence again, differently. You cannot see the Oort cloud. You can only see what falls out of it. That is not just a description of a clever method. It is a description of a single point of failure. Because if the only instrument you have for measuring a reservoir is the rate at which things drip out of it, then everything you conclude about that reservoir depends completely on that rate being typical. And if it is not, if you happen to be taking your measurements during an unusual period, then your conclusions are wrong, and there is nothing in the method itself that could ever tell you so. Let me walk through the inference chain properly, because it is short and it is load-bearing. Step 1. Count how many long-period comets arrive per year. We have been doing this, with increasing rigour, for a couple of centuries. Step 2. Build a simulation of a reservoir with some assumed number of objects in it, apply the galactic tide and see how many comets it delivers per year. Step 3. Adjust the assumed number in the simulation until the delivery rate matches the observed rate. Step 4. announced that as the population of the Oort cloud. That is where every figure you have ever heard about the Oort cloud comes from. 1 trillion objects larger than a kilometre, 5 Earth masses. All of it is the output of Step 4, and Step 4 is only as good as the assumption that Step 1 measured a normal year. And if Kaib and Raymond are right, Step 1 has been measuring a year that is running at roughly double speed. So the number comes down. Their own words. Prior estimates of the Oort cloud's population are likely a factor of 2 to 2.5 too large, and estimates based on the modern comet flux should be revised downward by a factor of 2 or more, which means the trillion becomes 4 or 500 billion. Every textbook figure moves, not because anybody was careless, not because a calculation was botched, not because of some subtle bias in the surveys, but because the single window we have was open during an anomaly, and there was no way to know. One point of precision, because I do not want to overstate what they actually claim. They revise the population, the number of objects. They do not revise the mass, and they are careful not to, because the relationship between how bright a comet appears and how much material is in it remains genuinely poorly understood. If you see a headline saying the Oort cloud is half as heavy as we thought, that is somebody extrapolating past the paper. But here is the part that makes me think this is more likely to be right than wrong, and it is the sort of quiet corroboration that is much more persuasive than any single result. In 2019, a group led by David Vokrulicki built one of the most careful models yet of how the Oort cloud assembled itself over 4.5 billion years. And when they ran it forward and asked how many comets it should be delivering to the inner solar system today, their answer came out too low. By a factor of 2 to 3. Their cloud simply did not produce enough comets to match what we observe, and they reported it as an unresolved discrepancy, a place where either the model or the observations must be wrong, and nobody knew which. Now put the two results side by side. Vokrulicki's model predicted a comet flux 2 to 3 times lower than observed. Kaib and Raymond say the observed flux is 2 to 2.5 times higher than normal. Those are the same discrepancy, seen from opposite ends. If the observed flux has been inflated by an ongoing comet shower, then Vokrulicki's model was never wrong. It was right, and the measurement it was being compared against was the thing that was off. A problem that had sat there unresolved for years does not get argued away. It simply stops existing. That is what a correct correction looks like. It does not just explain the thing it was invented to explain. It cleans up something else on its way past. And I want to sit with what this actually means, because I think it is the genuinely unsettling part of this whole story, and it is not the part anyone expects. Every figure you have ever been given about the Oort cloud, every trillion, every number in every documentary and every textbook and every classroom, was derived from a comet flux that was running hot because of something that happened before our species existed. The measurement was not sloppy. The people who made it were rigorous. They used the best available data and the best available models, and they got the wrong answer anyway, because the only aperture through which the region can be observed happened to be pointed at it during an unrepresentative moment. We were reading a fever chart and calling it a baseline, and it gets slightly worse when you remember what we established about the loss cone. Even in a completely quiet epoch, with no shower running at all, the observable part of that cone is less than 1% full for the inner region of the cloud, which means that in normal times we're not sampling the Oort cloud. We're sampling the thin outermost skin of it, the small fraction that the galactic tide can reach, and inferring the whole from that. The census was already fragile before anybody discovered that a star had walked through the middle of it, and there is one more layer of not knowing stacked underneath that, which I think completes the picture. The ratio between how much material sits in the inner cloud and how much sits in the outer cloud is one of the least settled quantities in the field. Published estimates for that ratio range from about 1 to about 200. That is not a disagreement about a decimal place. That is a 200-fold spread in how much of the reservoir is in the part we cannot observe at all. So the honest position on the largest structure in our solar system, 75 years after it was proposed, is this: we have never seen it. We know its population only through a single indirect channel. That channel has less than 1% throughput from most of its volume, and the throughput we've been measuring has probably been elevated by a factor of 2 for the entire span of scientific astronomy by an event we only identified in 2026, which reframes the promise in the title of this video, and I want to do that now rather than at the very end because the reframing is the point. When you hear that a star pierced our solar system and the danger is far from over, the natural assumption is that the danger is comets, that something is coming, that the sky is loaded, that there is an impact in our future with our name on it. And we're going to deal with that question directly in a moment, honestly, with the actual numbers, because it deserves a straight answer. But the thing that Star damaged was not the planet. It was the measurement. And a corrupted measurement is a stranger kind of problem than a rock, because a rock either hits you or it does not, whereas a corrupted measurement quietly deforms everything you build on top of it, for as long as you fail to notice, and there is no impact, no crater, no moment at which you find out. You just carry on being confidently wrong until somebody happens to plot an old column of numbers a new way round. Still, a promise is a promise, and the title made one. So let us do the arithmetic on the actual danger, because it turns out to be both smaller and more interesting than the version people reach for. Part 12. How dangerous this actually is. I am going to give you the answer first and then justify it, because I think that is more respectful than building suspense around a risk figure. The answer is that the increased comet flux from this encounter represents a very small increase in an already very small hazard, and that if you were making a list of things that might harm the human species, this would not make the first several hundred entries. That is the honest arithmetic. It is less dramatic than the setup, and the reason I still find it worth an entire section is that the way we know it is a genuinely good story about how science disposes of an idea it once took seriously. Start with the mechanics of what a shower actually is. The concept goes back to Jack Hill's in 1981, the same paper that gave us the inner cloud. A close stellar passage opens the starved region, and the released material arrives as a burst lasting a few orbital periods. Estimates of how intense that burst gets vary. The foundational 1987 work put the peak at around 20 times the ordinary rate, and more recent modelling has pushed that as high as 37 for the closest passages. Those are the peak figures, and the peak was 2 million years ago. We are in the long tail. Now the baseline hazard, which is the thing the shower is modifying. Objects around 1 kilometre across, roughly the smallest size generally thought capable of causing a global rather than a regional catastrophe, strike the Earth about once every 100,000 years. Objects around 10 kilometres across the Chicxulub class arrive about once every 100 million. But those numbers are dominated by asteroids, not comets, and that is the decisive fact in this whole section. The National Research Council's assessment in 2010, which remains the standard reference, put the comet contribution at on the order of less than 1% of total near-Earth object impact risk. Long-period comets specifically, the ones we have been talking about all night, the ones from the Oort cloud, contribute under about 1%. Asteroids outweigh them by something like 100 to 1, so run the calculation. The comet flux is currently elevated by a factor of 2. 2 times something that constitutes under 1% of the hazard leaves you with something that constitutes under 2% of the hazard. The needle moves, and it moves by an amount that is genuinely hard to care about. There is one published descent worth mentioning, because it is the only version of this story in which comets briefly become the main threat. The group led by Joy Asau, working with Abraham Loeb and Morgan McLeod, favours a much closer passage for the same star, as close as 2,300 times the Earth-Sun distance, rather than 6 to 10,000. At that distance, their modelling has the impact probability for kilometre-scale comets rising by an order of magnitude, to the point where it slightly exceeds the asteroid impact probability at that size. That is a real published result, and I am not going to wave it away. But note that it depends on an encounter 3 to 4 times closer than the comet evidence supports. that it is a different team reaching a different answer about the same star at the same date, and that both groups agree the same forthcoming measurement will settle which of them is right. And now the part of this subject with actual history behind it, because the idea that comet showers drive mass extinctions was once mainstream enough to appear in Nature twice in the same week. In April of 1984, two separate teams published back-to-back papers proposing that the Sun has an unseen companion, a faint star on an enormously long orbit that periodically passes through the Oort cloud, triggers a comet shower, and causes a mass extinction. One team was Whitmire and Jackson, the other was Davis, Hutt and Muller, and Muller's group gave the hypothetical companion the name it is still known by, Nemesis. This was not fringe work. These were serious scientists addressing a serious puzzle, an apparent 26 million year rhythm in the extinction record, published by Raup and Sepkoski that same year, which seemed to demand a periodic external cause. Both halves of that idea are now gone, and they went in different ways. The companion went first, and it went cleanly. In 2014, Kevin Luhman searched the WISE infrared survey for it. Infrared is exactly the right tool, because even a very faint cool object glows in the infrared, and WISE mapped the entire sky. He found nothing, and the nothing was thorough enough to rule out an object as small as Saturn out to 28,000 times the Earth-Sun distance, and an object as small as Jupiter out to 82,000. An actual star, or even a brown dwarf, would have been trivially obvious. There is no companion. That same result, incidentally, disposed of the Nibiru and Planet X stories at a stroke, since they require a body far larger than anything the search permits. The periodicity took longer to die, and it died of statistics rather than observation. In 1987, Stephen Stigler and William Wagner showed that the test Raup and Sepkoski had used was biased. It had a tendency to return an answer near 26 million years, whether or not the underlying data were actually periodic. Later work by Baylor Jones, examining the crater record directly, found periodicity strongly disfavoured across every dataset he tried, with the impact history best described by a constant probability rather than a cycle. A minority of researchers still argue for a signal, the mainstream does not. And Baylor Jones, the same person whose stellar encounter census made the 2026 paper possible, reached a conclusion in 2014 that I want to quote for balance, because it sits in productive tension with everything we have discussed tonight. Stellar encounters, he wrote, do not represent a significant threat to the terrestrial biosphere, nor are they a major source of Oort cloud perturbation. That is the considered mainstream verdict, from an expert with no stake in downplaying it, and it should be weighed against the excitement of a fresh result. But there is something quite lovely buried in this, and it is the turn I have been waiting the whole video to make. What the Nemesis idea wanted, and what the conspiracy version of it, the hidden companion, the concealed dark star has always wanted, was an agent. Something out there, deliberately, or at least systematically stirring the comets, and either unknown to astronomers or kept quiet by them. And the evidence has now delivered exactly that. There really was an object that really did reach into the Oort cloud and really did send a swarm of comets inward, and it really is still affecting us today. It is a G-type dwarf in Cassiopeia. It has been in the catalogue since 1852. It is 246 light-years away. It left 2.5 million years ago. It is not coming back, and nothing about it was ever hidden from anyone. The truth was not concealed. It was sitting in a column of comet orbital elements that nobody had happened to plot the right way round. There is one coincidence left, and I have to handle it carefully, because it is the single easiest place in this topic to say something false. The date of this encounter lands suspiciously close to a real transition in Earth's history. The base of the Quaternary, the boundary between the Pliocene and the Pleistocene, is formally dated to 2.58 million years ago. Major glaciation of the Northern Hemisphere began around 2.7 million years ago, and there was a genuine extinction. Work published in 2017 documented a Pliocene marine megafauna extinction at that boundary running at 3 times the background rate for the whole era, with about a third of megafauna genera lost and marine mammals down by more than half. There is even a third astronomical signal in the same window, an excess of a radioactive isotope of iron in deep ocean sediment, spread across roughly 1.7 to 3.2 million years ago, generally interpreted as the trace of a nearby supernova, a comet shower, a marine extinction, a supernova signature, all in the same window. And they are 3 separate, individually unproven threads that happen to overlap in time, and stitching them into a single causal story is the easiest mistake available in this entire subject. The researchers who documented the extinction concluded that the driver was the abrupt loss of productive coastal habitat, which is a sea level story, not an astronomical one. The team that connected the star to the climate transition claims only that it could plausibly be related, and nobody, in any peer-reviewed paper, has credibly tied any extinction event to a stellar flyby. So I'm not going to tell you the star killed the megafauna. The star did not kill the megafauna, as far as anyone can demonstrate. What it did was corrupt the only instrument we had for measuring the region it walked through. And the reason none of this is finished, the reason the danger really is far from over, in the only sense that can be defended, is that the next one is already on the calendar. We know which star, we know how close, and we know the date. Part 13, the one that is still coming. Its name is Gliese 710, and it is on its way. It is a K-type dwarf, an orange star smaller and cooler than the Sun, about 6/10 of the Sun's mass and a little under 6/10 of its radius. It sits in Serpens Cauda, the tail half of the constellation of the Serpent, about 62 light-years away, and at 9th magnitude you cannot see it without optical help. In every respect that matters to a casual observer, it is as unremarkable as HD 7977, which by now should be starting to feel like the theme of this entire subject. And in 1,292,000 years, give or take 23,000, it will pass through the Oort cloud at a distance of about 13,100 times the Earth-Sun distance. I want to pause on the fact that we can write that sentence. We know the date, not the era, not the rough window. The date, to a precision of a couple of %, computed from measurements that have already been taken by an instrument that has already been switched off. The next major stellar encounter of our solar system is a scheduled event. Let me also head off a garbling that has spread through popular accounts of this, because I have seen it repeated in several places and it is wrong by a factor of 100. You will sometimes read that Gliese 710 will pass within 16 light-years. 16 light-years would be about 1,000,000 times the Earth-Sun distance, further away than most of the Oort cloud, and further than 4 times the distance to the nearest star. The real figure is about 2/10 of a light-year, and honestly, the most human way to express it is in light days. At closest approach, Gliese 710 will be roughly 24 light days from the Sun. Voyager 1 will not be 24 light days out for another 20,000 years. The history of that number is itself a small monument to instruments getting better. Before Gaia, the best estimates put the encounter out near 60,000 times the Earth-Sun distance, far enough to be interesting and not alarming. Gaia's first data release brought it into about 13,400. The second gave 13,900. The third gives 13,100, with an uncertainty of only a few %, and an independent analysis this year lands at about 12,800. The encounter did not change. Our ability to see it did, and it will hit harder than HD 7977 did, despite being a smaller and lighter star. Here is why, and it is the payoff of the formula from earlier. Gliese 710 is slow. Its encounter velocity is around 14 kilometers per second. The typical passing field star crosses at somewhere between 46 and 53, so this one is coming through at roughly a third of normal speed, which by the rule that the impulse scales inversely with velocity is worth 3 to 4 times the gravitational kick for free. It will linger. It will spend thousands of years inside the region where it can do damage, leaning on the cloud the entire time. Put the mass, the distance, and the speed together into the standard measure of how disruptive an encounter is, and Gliese 710 comes out as the strongest perturbation of our Oort cloud in either direction of time, stronger than anything we know of in the past, stronger than anything else forecast. When astronomers recalculated it with Gaia's data, the number came out 20 times larger than the pre-Gaia estimate. It went from a footnote to the most significant stellar encounter in the solar system's known history, on the strength of one satellite's measurements. So picture it. 1.25 million years from now, somebody or something stands outside on a clear night on this planet. The constellations are gone, not dramatically, just quietly wrong. Every familiar pattern pulled out of shape by 1 million years of stellar drift. The plough unrecognizable, Orion dispersed. There is no arrangement in that sky that anyone alive today would know. And there is an orange point of light in it that is brighter than everything except the Moon and Venus, magnitude -2.7, brighter than Sirius, which is the brightest true star we have ever had. Brighter than Jupiter at its best. It is not a moon, it does not light the ground, but it is unmistakably the most prominent single star anything on Earth has seen in the whole existence of complex life, and it sits there for thousands of years, drifting imperceptibly, while whatever is looking at it invents and forgets whatever it invents and forgets. If that thing has astronomers, they will be able to do exactly what we have just done. They will measure it and calculate its path, and work out that up above their heads, in a region they also cannot see directly, something on the order of 0.1% of their Oort cloud is being pulled loose. Published estimates say up to 0.1% of the cloud's comets could be removed outright, and up to 0.1% pushed onto orbits that eventually become visible, producing a comet stream perhaps 35 times richer than earlier work suggested, which works out to something like 10 new comets a year, sustained for 3 to 4 million years, and not peaking until roughly 1 million years after the star is gone. Which means those astronomers will also be able to work out that they will not live to see it. The first of those comets will not arrive for 1 million years after the encounter. Everything they build will be gone. There is one more detail about Gliese 710 that I find quietly enormous. Because it is a K-dwarf, it burns its fuel far more slowly than the Sun does. Stars like it live somewhere between 15 and 45 billion years against the Sun's 10. And our own Sun will render the Earth largely uninhabitable in another 1 or 2 billion years, not by dying, just by brightening. So if Gliese 710 has planets in its habitable zone, and a star of that type very plausibly does, those worlds will remain habitable for billions of years after Earth has stopped being an option. Which brings us to the speculation, and I am labelling it clearly as speculation, because that is the rule here. The arithmetic is the seductive part. Proxima Centauri, the nearest star, is about 268,000 times the Earth-Sun distance away. A star passing at 10,000 is 27 times closer than that. Voyager 1, with no propulsion at all beyond what it was given in 1977, would cross 10,000 units in about 2,800 years. It would take about 75,000 to reach Proxima. To get to Proxima in the same 28 centuries, you would need to travel at something like 456 kilometers per second instead of 17. And since energy scales with the square of speed, that is roughly 700 times the energy per kilogram. Leaving, meanwhile, is nearly free. Escape velocity from the Sun out at 10,000 units is 0.4 of a kilometer per second, less than a rifle bullet. So a passing star is, arithmetically, the cheapest interstellar destination that will ever be available. The catch is that arriving is the expensive part, not departing. The star is moving at 26 to 30 kilometers per second relative to us, and anything hoping to stay with it rather than merely wave as it goes past has to match that. And the honest state of the literature is thin. There is a peer-reviewed paper from 2022 arguing that a particular kind of sail could make migration during close stellar encounters take under 1,000 years. There is another from the same year proposing we look for technosignatures on free-floating planets, on the theory that a civilization might ride a world rather than build a ship. That is roughly the extent of it. Nobody has proposed Gliese 710 as a transport opportunity in a journal. It is an idea, not a plan, and I am telling you about it because it is a real idea and not because anyone has costed it. So, the title of this video made a promise, and here is the payoff, in 2 parts. The first part is the straightforward one. The comet shower that HD 7977 started is still running. Objects loosened from their orbits before our species existed are still falling inward, arriving now, arriving next century, arriving for another 3 to 10 million years before the rate settles back to whatever normal is. When astronomers discover a bright new comet in the 2030s, there is a reasonable chance they are looking at a piece of debris from an encounter that predates the human genus. That is not finished. It has barely started to fade. But the second part is the one that matters, and it is not about comets at all. The real casualty of that encounter was our own picture of the solar system. We built our entire census of the outer solar system, the trillion objects, the mass, the structure, the numbers in every textbook, out of a comet flux that was running at double speed because of something we did not know had happened. And the harder problem, the one that does not go away even after we correct the number, is that we still cannot reliably tell the difference between a solar system at rest and a solar system still ringing from being struck. Because look at the rates. Encounters strong enough to shift the average comet flux by 10 or 20% happen every 5 to 10 million years. Passages as close as 10,000 units happen every 50 million or so, which raises a genuinely uncomfortable possibility that there is no quiet baseline at all. That the calm, tide-dominated solar system in the textbooks is not a description of reality, but an artifact of having a 300-year observing window and needing something to call normal. That what actually exists is a sequence of disturbances at different stages of fading, overlapping one after another, and we happen to be standing inside one. We may never have measured the solar system at rest. We may not know what that looks like. The good news, and I mean this, is that this is a story with dated test in it rather than an argument that can run forever. The first is the 2nd of December, 2026. That is when Gaia's 4th data release is published. 66 months of data, 2 billion stars with a high-quality solution, and critically, models that can properly handle stars that are not single. Kaib and Raymond wrote a prediction into their paper. The new data should favour an encounter distance of 6 to 10,000 units for HD 7977. If it does, this result gets much stronger. If the star turns out to be a binary whose wobble has been masquerading as motion, the reconstruction collapses. Kaib's own words were that the nice thing about the prediction is that it will be testable pretty soon. The second test is already running. The Vera Rubin Observatory began its 10-year survey of the southern sky on the 29th of June, 2026, and over that decade it is expected to take the number of known comets from around 4,000 to around 10,000. The sample of pristine first-time comets, the 107 objects this entire argument rests on, should grow by something like an order of magnitude. Either the evenness holds up in a sample 10 times larger, or it dissolves. And I want to end by giving the last word to the doubters, because they have earned it. An astronomer at Leiden named Simon Portuguese Zwart asked about this work, said that the conclusion we are in the tail of an enhanced comet shower remains up for debate, and that the result could be a one-off arising from the specific conditions simulated. His objection is technical and fair. They modelled a single realisation of the Oort cloud with 1 million bodies, and he would want 100 million and multiple configurations. He also said, in the same breath, that he was happy the authors were exploring it. And Sean Raymond, one of the authors, said this about his own paper. Like many other works that simulate long-period comet production, we find that our comet's orbit sizes are not a great match to the observed distribution. It is possible we are missing some important physics, and it is conceivable that this has caused us to misinterpret comet orbit data. That is a scientist volunteering the weakest part of his own result. Hold on to that, because it is what the process looks like when it is working, and it is almost never what you see in a headline. So here is where we finish. 2 dates. 1,292,000 years from now, when an orange star arrives and starts the whole thing over. And the 2nd of December 2026, when we find out whether the last one happened the way we think. The gap between those two numbers is the whole feeling of this subject. We can see 1,000,000 years ahead and 2.5 million years behind. We can name the star and the date and the distance, and we cannot yet say for certain whether the thing that shaped the comets in our own sky was one particular ordinary star in Cassiopeia, or a mistake in our understanding of the shape of the cloud. Another star pierced our solar system. And the danger, the real one, the one that was never about impact, is far from over, because we are still inside the wake, still reading instruments that event distorted, and still unable to tell a solar system at rest from one that is quietly ringing. 2.5 million years ago, something on this planet looked up and saw a second light in the sky, and had no idea what it meant. We know exactly what it means. We are simply too early to be sure.